We will now conclude our discussion of inverse functions with a quick way to check whether a function has an inverse or not. It's quite analogous to how we checked if the plot of a curve in the plane was the plot of a function. We checked that with what was called the vertical line test. We'll look here at the horizontal line test. So recall that one can check if a plot in the Cartesian plane is the plot of a function via the vertical line test. So we looked at some purported function and we drew vertical lines. And if it intersected the plot only once, it was a function. And if there were multiple intersections, it was not a function. So this is an example of failing the vertical line test. The horizontal line test is exactly the same, except it checks for the existence of an inverse function. So here, every horizontal line intersects the function only once, so an inverse exists here. Here, for example, there are horizontal lines that intersect in multiple places. So an inverse doesn't exist without restricting the domain. If I had, for example, only looked at this function for x greater than or equal to 0, I wouldn't have a problem with the horizontal line test. But because I allow for a full domain, there are points that get sent to multiple points that get sent to the same output, which will have a problem for the inverse function. So let's just look at a few examples. Let's go to that one again. Let's say y equals x squared. Okay, so what would we think that the inverse function for this would be? Well, we'll switch the roles of x and y. We'll try to solve for y. But the problem is that y is then equal to plus or minus the square root of x. So we have an issue here. Let's say absolute value. Square root x. So the issue is that this is not really a function. This is something that takes on two values. So this is y equals plus or minus square root of x. So what we have to do is make a choice of branch of the square root. And we will typically take this one. And in that case, if we define this to be the square root, then that is the correct inverse function. Okay? So in this case, we would say f of x equals x squared for x greater than or equal to 0 has inverse f inverse of x equals square root of x, also defined for x greater than or equal to 0. So in this case, the picture is something like this. So here's f, and then here is its inverse function. So when I restrict the domain of x squared, I am able to get an inverse. Otherwise, I fail the horizontal line test. Right? So if I plot f of x equals x squared, the horizontal line test is going to be failed unless I restrict the domain. And we see that sort of manifested up here as well. Essentially, having the horizontal line test be passed on the function guarantees that what you think its inverse should be is actually a function, that it itself will pass the vertical line test. And again, if we look back at our plot, we see that here, that this parabola f of x equals x squared fails here, fails the horizontal line test, which means its sort of natural inverse fails the vertical line test. So, but if we cut off the domain of x squared, then we get a unique inverse function. Let's look at one more thing like this. Let's take f of x equals x cubed. We'll say, does it have an inverse? We'll try. So y equals x cubed. We switch the roles of x and y. Well, y should be equal to the cubed root of x. What's the picture for that? Well, it actually is defined everywhere. It looks like this. And unlike the previous example, this passes the vertical line test. So the inverse, what we think the inverse function should be, actually exists as a function. And this is also manifested by looking at the horizontal line test on f of x. So here is f of x equals x cubed, and this passes the horizontal line test. Every horizontal line intersects at only one point. So what this means is that either I could try to compute the inverse function explicitly and see if it exists as a function, or I can just check the horizontal line test. So this passes horizontal line test, which tells me that f inverse exists. So as a remark, x squared doesn't have an inverse on its whole domain. We needed to chop off the domain. But x cubed does. And these are very kind of archetypical examples of how inverse functions get tricky. X squared didn't have an inverse because it failed the horizontal line test. So what I naturally wanted to do as the inverse function was not a function. It itself failed the vertical line test. What I had to do for x squared was chop off its domain so that it would pass the horizontal line test on that domain. For x cubed, this wasn't a problem. It passed the horizontal line test everywhere, so the natural choice of inverse function did exist as a function. The cube root is defined for all numbers and it has a unique output. The square root function is not defined for all numbers, and there's sort of two natural branches of it. And that's what's impeding the existence of an inverse function here.